In the last video, we took a look at cross-sections and contours. Contours are also called level surfaces of a three-dimensional function that allows us to sort of splice or slice a three-dimensional surface and create two-dimensional graphs. In this shorter video, we'll consider a real-world model, and we'll look at the cross-sections and see what that data reveals to us. This problem says the number of prisoners in state prisons in the US can be approximated by n of xy equals negative 540 plus 7.5x plus 2.5y minus 0.01 xy, 1,000 inmates. Now this right here, notice we have a product between x and y. Sometimes this is called an interaction term. And it's an interaction between x and y. They get multiplied together. So the output of this function, if I input a value for x and y, it will tell me how many inmates there are as an approximation in the United States. Well, x in this context is the number in thousands that are in federal prisons, and y is the number in thousands in local jails. Okay, so depending on how many federal prisons and local jails we have, we can determine how many prisoners there are. In other words, the more jails and the more federal prisons we have, the more prisoners there can be. So let's analyze cross-sections for x, for y, and then look at contours for n. So first thing we're going to do is let's just pull up a graph of this function. So here I've defined my function, and the first image we may get may look a little hard to interpret. I've already zoomed out a little bit, but let's just go ahead and continue zooming out. You could use the zoom out button here, or you could use the roller on a mouse, and you can kind of see that it has a funky shape, and the more we zoom out, the more interesting that shape gets. And that's pretty hard to interpret right there. I mean, the height of this tells me how many prisoners there are, so anything below the xy plane simply doesn't make sense. And also I should really just focus on the positive x-axis and the positive y-axis, which is actually just this little quadrant right here. Okay, hard to understand what's actually going on there. So let's go ahead and look at some cross-sections and try to understand what we're looking at. So first of all, when we hold x at positive 1 versus positive 2 versus positive 3, we're going to go ahead and just use Desmos for this, because it's going to be a lot easier for us to visualize what we have going on, and we're not going to often plot these by hand. So I'm going to go ahead and type in negative 540 plus 7.5x plus 2.5y minus 0.01 xy. And I'm going to call this, I'm not sure I'll be allowed to do this. All right, there I have a function defined, but I'm not going to be able to plot this in 3 dimensions. This is a 2-dimensional grapher. So we said let's hold x constant at 1. Okay, we're going to hold x constant at 1. And I'm going to plug in 1 for x over here as well. And it doesn't really show me anything. So I have to get a little bit more creative here. The graph that I want is this one right here. So I'm going to actually turn this into a text entry, and because I can only use y and x when I'm using Desmos, I'm gonna let y represent the output, which is actually z in this case. Okay, so I'm gonna use x and y to actually represent z and y. Okay, I'll explain this in a second. So I'm gonna type in negative 540 plus 7.5 times 1 plus 2.5. Now for y, I'm going to use x, because I want that on my horizontal axis, minus 0.01 times x times y. All right, I know that seems strange to do, but let's go ahead and zoom out and see what graph we get. On the vertical axis, what we actually call the y-axis, this is n, the number of prisoners in thousands. On the horizontal axis, what I have is the value of y, which is the number of local jails. And when I label these, now I can see that as the number of local jails increases, the number of prisoners in thousands increases linearly. That appears to be a straight line. All right, now let's go ahead and repeat this same thing. I'll just copy this and paste it, and now I'll just change the value of what is actually x to 2. Okay, now I might have to zoom in a bit because it might be hard to see the difference between these two graphs, but you could see that they are both linear functions, though one appears to be shifted. Let's do the third graph and plug in 3. And now let's take this and put it back into our demonstration. So here we have it, and now let's focus on unpacking or interpreting what's going on here. We said that this was for x equals 0, x equals 1, and x equals 2. And this is x equals constant. And the relationship that we're looking at is the number of prisoners versus the number of local jails. Well, let's start with x equals 0. That means that there are 0 federal prisons. And we can see that as the number of local jails increases, the number of prisoners increases as well. Okay, we can say that much. When we have x equals 1 federal prison, we see a similar relationship. But the difference is that, for instance, when there are 215 local jails, notice that there are about, we'll just say right about 3,000 prisoners. And I'm just mapping that over here. This is about 3. However, for that same number of local jails, but with having 1 federal prison, notice that we're now at about 8. That point right there is approximately 8,000 prisoners. So this suggests that the more local prisons you have, the more prisoners you're going to be able to have in these prisons. But if you have more federal prisons, for that same number of local jails, you can house more prisoners. When you have x equals 2 federal prisons, notice that that number is right at about 13. So we have approximately 13,000 prisoners. So the more federal prisons we have, the more prisoners we can have, while still having the same number of local jails. So let's say that. With more federal prisons, we can have more prisoners for the same number of local jails. We can also say that as the number of local jails increases, so does the number of prisoners, right? Because the more local jails we have for that fixed number of federal prisons, well, with only 1 federal prison, there's only so many prisoners you can have in those federal prisons. So we're here relying on increasing the number of local jails. We can see that in all of these instances, the number of prisoners goes up. Now let's do the exact same thing, but now we're going to hold y constant. Okay, so I'm going to put x back in here for the ones, and then remember this is really just our container for y, so I'll put in a 1 there, and I'll put in a 1 here, and now I'll press enter, and some things have changed, but let's go ahead and do the same thing for all of these, and put in a 1 for the y. It should be 2. And you can see those graphs disappeared, right? The only one that's still showing is the one for x equals 3, because they're going to be different graphs. They're not going to look exactly the same. In fact, there you can see them. There's still a linear relationship, but our horizontal axis is now the number of federal prisons. So let's change this one here as well. Again, there's just some bookkeeping that we're having to do here. We're always having to treat our input variable as the one that's not being held constant. Okay, so now what we're looking at is the relationship between these three. And instead of this being y, the number of local jails, this is x, the number of federal prisons. So here we have that graph, and now once again what we're looking at is still the number of prisoners, but we're looking at it versus the number of federal prisons while holding y equals the number of local jails while we're holding that constant. So all this exhibits is the relationship between prisoners and the number of federal prisons. So this is for y equals 0. If we have 0 local jails, we can look at, okay, as you increase the number of federal prisons, how many prisoners will you have? This is y equals 1, and this is y equals 2. So once again, the more local jails you have, the fewer federal prisons you need in order to house the same number of inmates. So like here, for example, notice that if you have 72 federal prisons, but 0 local jails, you can only house 2,000 inmates. For 72 federal prisons, but 1 local jail, you can now house, that appears to be about 3,500 prisoners. For 72 federal prisons and 2 local jails, you can house about 5,500 prisoners. But what we can say is, once again, so in this same kind of vein, we could say with more local jails, we can have more prisoners for the same number of federal prisons. And as the number of federal prisons increases, so does the number of prisoners. Finally, let's take a look at the relationship between y and z while holding, x and y while holding z constant. So we want to look at this for 100,000 prisoners. So this is a little bit easier to do because now we don't have to be playing around with x and y. Now we're literally looking at x versus y. And we'll do this for 100, 200, and 300. So let's change our axes. X is the number of federal prisons. The vertical axis is y, the number of local jails. And this graph may make a little bit more intuitive sense. Let's go back to our local picture and zoom out a bit. And now things get a bit more interesting, notice. And let's try to figure out what this graph tells us. Well, here we're holding n equals the number of prisoners. So this is holding the number of prisoners constant. This red curve is for 100,000 prisoners. This is for 200,000 prisoners, and this green one is for 300,000 prisoners. And this is going to tell us all the different ways in which we could house or give a place for 100, 200, and 300,000 prisoners just by determining the number of federal prisons and local jails. So if I know, for example, I only have a certain number of federal prisons, then I can figure out the corresponding Y value that will allow me to house a certain number of federal prisoners. For example, I'm going to pick on this point right here because it's kind of close to an integer pair. If I want to house 300,000 prisoners, one way to do that would be to have 100 federal prisons and 60 local jails. But if I still wanted to have 60 local jails, but only house 200,000 prisoners, well, that means with 60 local jails, I wouldn't need as many federal prisons, right? Because I have fewer prisoners, so I could still do it with 60 local prisons, or 60 local jails, but I would only need, about approximately 85 federal prisons, and I could have a place for all 200,000 prisoners. But let's say I only had 100,000 prisoners and 60 local jails. Well, in that case, I would need only about 70 federal prisons while maintaining those 60 local jails, and now I could put 100,000 prisoners in there. So every time we increase the number of prisoners, our next level curve will be, maybe more like this for 400,000, because now for the same number of local jails, I would actually need more federal prisons to give home to, say, n equals 400,000 prisoners. And all of these level curves are just going to keep moving that way as I increase the number of prisoners that I have available. So at the end of all of this analysis, what we've really figured out is that as you increase the number of local jails while holding the federal prisons constant, then you increase the number of prisoners that you can house. This picture tells us that if we have a fixed number of local jails and only increase the number of federal prisons, the number of prisoners we can house goes up linearly. However, here we could say as we increase the number of federal prisons, in order to, for example, have 300,000 prisoners, if we increase the number of federal prisons, and we could see that we need fewer and fewer local jails, and we can still get n equals 300 prisoners housed. It's not a linear relationship. We can see that it's curved. If we want n equals 200 prisoners, well, if I increase the number of federal prisons, I'm going to need fewer and fewer local jails to house those 200,000 prisoners. And so this just gives us all the different ways in which we could give a place for a certain number of prisoners.